Can you recall the name of the error correction mechanism you have studied in the computer networks? Anyone can recall the name of the error correction mechanism? Yes, pardon. Louder, please. So Hamming code. Hamming code is the error correction mechanism, right? So we'll try to understand now. Remember, the error correction mechanism is somewhat complex compared to error detection mechanism, because the error correction involves error detection plus the correcting the corrupted bit, right? So because error correction is somewhat complex, right? Error detection just identify whether message is modified or not, right? But error correction has to identify whether message is modified or not, corrupted or not. If it is corrupted, which bit is corrupted, then that bit should be modified. So as part of this error correction, we will try to understand the Hamming code. As I told you, whether it is a error detection mechanism or error correction mechanism, both will add some extra bits. We call them as redundant bits or check bits, right? Both will add redundant bits to the original message. But if you see the error detection mechanisms, in most cases, the redundant bits are appended at the end of the message. Think about CRC. So CRC will be appended at the end of a message. Think about checksum. Checksum will be appended at the end of a message. I have understood, right? In most cases. But in the Hamming code also make use of redundant bits, but redundant bits won't be added at the end of the message. It will be added in a specific places, right? So that keep in mind. So in which positions the redundant bits will be added, we'll try to understand one by one with the algorithmic steps with the example, right? The first step you have to understand in the Hamming code is it is a error correction mechanism. It is not detection, it is correction, means it also detects and corrects that error, right? Error correction mechanism. Second point, see now in CRC, how many redundant bits are added in the context of CRC? Can you recall? How many redundant bits will be added in the context of CRC?
Based on the degree.
Based on the
Degree.
Yes, so based on the polynomial generator degree, right? Same scenario here. Here, number of redundant bits will be added. There is a formula here. So try to remember this formula. Think about the number of data bits given equal to m. Data bits, m bits. Message is of length m bits. The number of the redundant bits to be added is assume r. Redundant bits assume r. Right? The formula, you have to compute r in such a way that by satisfying the formula, 2 power r greater than or equal to m plus r plus 1. So this is the formula. Based on this formula, you have to find out the r. M will be given to you. Whether remaining students are there or not. How can you? Nikhil Singh, are you there?
Yes, sir.
Yeah, please turn on your camera so that you can feel like physical class. Does it remain? It is like zigzag fashion. Nikhil Singh. Now think about, suppose think about m is m equal to 7. M equal to 7. Yeah, can you tell me the R value? If m value is 7, what is the R value? What is the R value? Now, is R value unique or not? So since it is not equal to, it is like greater than or equal, inequality, you can find more than one R value, such a way that this equation is satisfied. I hope understood, right? But among those, choose the minimal R value. The meaning is, now think about m equal to 7. Take like if R equal to 1, assume R equal to 1. What is the right hand side? 2 power R, 2 power 1, 2 greater than or equal to 7 plus 1 plus 1. So what is this value? This is 9. So this is in fact wrong, right?
R is 4.
R equal to 4. So now think about R equal to 3. Now what is the value right hand side?
8.
8. Or left hand side? 7 plus 3, 10, 11.
11.
This is also wrong, right? R equal to 4. R equal to 4. 2 power 4.
16.
16 greater than or equal to 7 plus 4, 11 plus 1, 12. I have understood, right? So here R equal to 4, this inequality is satisfied. That is the minimal R value. I have understood, right? So now based on this equation, find out the R value such a way that choose the minimal R value. Now in this example, R value is 4, right? So I will erase this part. So now R value is computed, R value is 4. Yeah, Nicola, is it Nicola, not Nicola. Himaza, is it clear, right, for you?
Yes, sir.
Yes. So R value is 4. For the m equal to 7, R equal to 4, right? What is the length of the data to be sent? Data to be sent. What is the length of the data to be sent? Louder, please. I didn't get. Data to be sent to the receiver. Receiver receives of the, what is that length? You forgot? That is only now I told you, right? See, the given data bits, or we also call it as data word, right? So you are given data word, right? Based on the given data word, you have to find out some check bits or redundant bits, right? You have to add these check bits or redundant bits to the data bits. Then finally you will get a message. Finally you will get the total message to be sent, right? That we call it as code word. Try to understand I'm using now formal terminology. So the message bits, message plus your redundant bits, or we also call it as check bits, redundant bits. right? Message also call it as data word, right? This is in fact your original data. Plus you are appending some more bits for correction or detection. The entire thing, this message plus redundant bits, technically we call it as code word. Are you getting? Because you are appending error detection code or correction code based on the which mechanism you want to use. I have understood. So the question now, formally, what is the code word length here? 11. I have understood, right? So try to understand the different terminology. So that the length of the data to be sent, it is nothing but the code word length. So the length of the code word is 11. Yeah. Is it okay, right? So far. Now we will try to understand how to find out that code word exactly. As of now, we have computed the length of the code word. How to compute the exact bits, right? With example. Assume the message. Assume the message given is 7 bits of message. Think about the message 1 1 2 3 5 zeros 1 1 5 zeros 1, right? How many bits are there? 7 bits message, right? So this here small m, assume the number of data bits equal to 7 here. We have already computed the number of redundant bits should be 4 based on the above formula, right? The Hamming code tells you there are different rules in the Hamming code. In fact, you already know the code word length is 11. So I am just drawing that code word. There are, in fact, code word is having 11 bits, right? I will just draw that each cell is a 1 bit. 1 2 3 4 5 6 7 8 9 10 11. Yeah, this is the code word. The first step here in the Hamming code computation, you just give the that position like 1 2 3 4 starting from 1. Always start from the least significant bit. This is your LSB, already you know, least significant bit. This is your MSB, right? Number those positions of bits starting from 1. Again you have to number starting from the LSB, right? This is the bit position 1, bit position 2, bit position 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, is it clear so far? I have understood, right? So in the Hamming code, first step is the write all bit positions starting from 1, right? Bit positions starting from 1. Starting from 1. Remember, always you have to give 1 to your least significant bit, but not MSB, right? Always consider your LSB as the 1. Right? Step 2, the first step is over. I have already given, right? Step 2, in fact, all bit positions that are powers of 2. So the bit positions that are powers of 2 are marked as data bits. Sorry, are marked as redundant bits. powers of 2 in that bit positions, we have already give the bit position number. We have already given the numbers for bit position starting from 1. You can see the powers of 2 positions, right? Yeah, powers of 2. Can you tell me now? 2 power 0, powers of 2. 2 power 0, 1. This is in fact power of 2, right? 2 power 1, powers of 2. 2 square, powers of 2, classes. Sorry. Yeah, 2 power, next one. 8. These are all the powers of 2 bit positions, right? So powers of 2 bit positions are nothing but your redundant bits, right? So for redundant bits, we have to compute later. So far I am just writing R. R stands for these are all your redundant bits or capital R, whatever it is. Oh, already we have given small r, right? So rather I am using capital R. So this is your redundant bit. This is your redundant bit. Redundant bit we also call here parity bit. But here parity, why it is called parity, you will understand later at the end. Right? We also call it as parity bit. Or we also call it as check bits, right? So the 3 names. Redundant bits also call it as check bits or parity bits. Right? So with the name of parity, I want to make you more understandable, I want to give these names as this is in fact parity bit 1, parity bit 2, parity bit 3, parity bit 4. I hope understood, right? So there are, you have to compute 4 redundant bits or 4 parity. Both are same only. But try to understand with R notation. I am using 2 notations to make you more simpler. First parity bit is in the position first only, right? So in the R notation, R1 here, 1 tells you the position of the redundant bit. Here 1 tells you the serial number 1, 2, 3, 4, 5 and so on. Is it clear so far? I am using 2 notations, general notations. 4 parity bits I have to compute. I can just call P1, P2, P3, P4 and so on. But in the R notation, the index or the subscript tells you the position of that redundant bit. Yeah, is it clear, right, so far? Okay. So this is about the second step. Third step, remaining bits other than powers of 2 are treated as the data bits or message bits, right? Remaining bits, remaining bits are treated as remaining bits are your data bits or message bits. Right? Is it clear? Yeah. So based on the step 3, what is the message given to us? This one, right? So remaining all bits are your message bits, data bits. So I will just fill up now the message 1, 0, 0 here. How many zeros? 1, 2, 3, 4, 5 zeros. 5 zeros, 1. Are you getting? See, remaining how many bits are empty, 7 bits only, right? Because totally we have already seen m equal to 7, r equal to 14, totally 11. So 11 bit positions. Among 11 positions, we have find out the which positions are redundant bit positions. So as per the Hamming code rule, powers of 2 are marked as redundant bit positions, right? So already I have marked. Already message is given to you. So just based the remaining bits are message related bits, just fill up that message. Is it okay? Now what is our goal? Our goal next is we have to compute what is the R1 value or P1 value, R2 value, R4 value, R8 value. I hope understood. We have to now compute the parity bit values or redundant bit values, right? There is again different rule here. The fourth step, computing the P1, computing the rule for computing P1 or R1. Note down this rule. I will just explain. P1 covers all the bit positions. P1 covers all the bit positions whose binary representation, P1 covers all bit positions whose binary representation includes a 1 in the LSB, includes a 1 in LSB, means in the first position, right? So what is this meaning is, so if you want to compute the P1 value, first see, like there are 11 bit positions, right? If you first you have to write all these positions in the binary format. So that is, we will try to understand what is this step is. So first we have to write, so there are in fact 11 bit positions. First we have to write all these bit positions into binary value. So I will write here. There are in fact 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Can you tell me the binary? This is the decimal, right? These are all the decimal bit positions. Can you tell me the binary equivalents? 1 only, right? 1 is 1 only. 2, 1 0. 3, 1 1. 4, 1 0 0. 5, 1 0 1. I have understood. 6, 1 1 0. 7, 3 1. 8, 1 0 0. 9, 1 0 0 1. 10, 1 0 1 0. 11, 1 0 1 0 1 1. I have understood. I will write this 1 1. I can write like a 0001, right? So each one, if I write like a 4 bit values, I can write like this. right? Yeah. Now recall that rule. To compute P1, you have to consider all the bit positions. You have to consider all the bit positions in the binary representation whose LSB. What is the LSB? LSB is your first bit position, right? Whose first bit position is having 1, right? To compute P1, P1 here 1 stands for. So in the binary, whatever that position, binary format, whose LSB is 1, if this LSB bit is 1, consider that bit. So this LSB is 1 or not? First bit is 1, right? Consider this bit. I am now putting tick mark. This LSB is 1 or not? This LSB was 1 or not? No, this is not 1, right? First bit is not 1. Here first bit is 1. Consider this bit. This is not 1. This is 1. Consider this bit. Consider this bit. Consider this bit. Consider this bit. I have understood. So if you want to compute P1, consider all those bit positions whose LSB is 1. That is the rule. So what are all the bits we are considering? Alternative, right? 1, 3, 5, 7, 9, 11, right? So I will mark now. Yeah, can you tell me by using this only these bit positions, which string we will get? So you have to consider 1, 3, 5, 7, 9, 11, right? So considering all those bits, I will now I will make you, I will use this color. I will just put a dot mark. So this bit we have to consider, and this bit we have to consider, right? 1, 3, 5, 7, 9, 11, right? All the dotted bits we have to consider. Yeah, what is the string formed using those bit positions? Can you tell me? 1, 0, 0, 0, 1, R1. I hope understood, right? Right? Yeah. Now rule, to make this string even parity. So try to understand why it is called parity bit. To make this string even parity, can you tell me the R1 value? 0. R1 means only one bit. 0. I have understood, right? To make this bit, to make this string even parity, R1 should be 0, right? So that is your R1. So now you have computed P1 or R1 value is 0. P1 or R1 value is 0. I have understood, right? This value is 0. I hope. Now just have a look at entire so far we have computed only R1, right? So now we have to focus on R2, right? So far just have a look at entire procedure so far regarding Hamming code. Any doubt so far? Yeah, can you proceed further? Pradyumna, Nikhil Singh, are you following or not? Yeah, is it okay? Clear? Can you proceed further? We will focus on now the rule for computing the parity bit 2, P2. Yeah, to compute P2, the rule is, see, like to compute P1, the rule is consider the bit positions whose LSB, whose LSB is 1. I hope got an idea, right? So if you want to compute P2, you have to consider all bit positions whose second bit from LSB, whose second bit is having 1. Consider all bit positions. I hope understood, right? So try to note down. To compute P2, you have to consider all bit positions whose second bit from LSB is having 1. Right? Yeah, can you tell me now what are all the bit positions I have to consider?
2. And second one.
Second one,
Sixth one. No, third one. Also.
third one also, right? So the second bit is 1 here. This no,
6, 7,
6, 7,
10, 11.
6, 7, 8,
10.
9 you have to leave, 10,
10, 11.
10, 11. So you can see a pattern here, right? In the earlier, it is like we are taking like interleaving fashion. Here, we are leaving 2 bits at a time. I have understood. You can see a pattern here. So now focus on these bits 2, 3, 6, 7, 10, 11. So 2, 3, go to your yeah, I will just mark here. So 2, 3, 6, 7, 10, 11. Using these bit positions, what is the string form?
P2.
Just give a minute. I will. Yeah, using these bit positions. Yeah, what is the string form?
P2.
P2.
The second one is.
This one, like what are the marked bits? 1, 0, 0, 0,
1.
1, 0, 0, 0, 1, P2 or R, right? I have understood. So 1, 0, 0, 0, whatever the marked position, the string formed is 1, 0, 0, 0, 1, P2 or R2, whatever it is. Right? Yeah, now the same rule. To make the string even parity, what is the R2 value? 0, right? R2 value or P2 value, right? So this is in fact again 0. This is 0. The R2 value is also 0. I have understood. Similarly, we'll go for now further. The further, that is P3. P3. This is also called as R2. P3 also called as R4, right? Here only difference will come. P3 means if you want to compute P3, you have to consider all bit positions whose third bit from LSB is 1. You have to consider all bit positions whose third bit, see here this means, right, whose third bit is 1 from your LSB, right? Yeah, now can you tell me what are all the bit positions I have to consider based on
7.
the 4, 6, 4, 5, 6, 7, right? 4, 5, 6, 7. The third bit is 1. Here only you can see the third bit is 1, right? You cannot see the remaining cases. So we have to consider only 4 bits. That is 4, 5, 6, 7. I hope you got an idea, right? So now I will mark here. I will mark here 4, 5, 6, 7. Four, 5, 6, 7. Yeah, using these bit positions, what is the string form?
0, 0, 0.
3 zeros,
And P.
3 zeros, R4, R4, right? To make this even parity, what is the R4 value? 0, right? So here R4 value is also 0. Got an idea? Is it okay? Now we have to compute one more bit rate, that is P4. I hope now you have understood the rules. Now if you want to compute if you want to compute the P4, if you want to compute the P4, the rule is you have to consider all bit positions whose fourth bit, try to understand, whose fourth bit is 1 from the LSB, whose fourth bit is 1 from the LSB. Yeah, can you tell me now what are all the bit positions I have to consider?
8, 9, 10, 11.
8, 9, 10, 11, right? I will put tick mark here. 8, 9, 10, 11. I hope now see, that's why I have making use of two notations, right? P1, P2, P3, P4, R1, R2, R4, R8. In the context of R, that subscript tell you the position, right? I have understood. In the context of P1, P2, P3, that is a general like the first parity bit, second parity bit, third parity bit, fourth parity bit, and so on. While computing Pn parity bit, you have to consider all bit positions in the binary representation whose nth bit is 1 from the LSB. I hope understood. Yeah, now based on this rule, I will mark 8, 9, 10, 11 in the original here. Eight, 9, 10, 11. So 8, 9, 10, 11. Yeah, using these bit positions, what is the string form?
1 triple 6, 1 double
1
0
double
R.
0 R8. So 1 double 0 R8. To make this even parity, what is the R8 value? 1. Right? So R8 value is 1. So I will write here R8 value is 1. So yeah, as of now, we have seen these all the things happen at sender side, right? I have understood. Sender side only we are seeing. Sender will compute the Hamming code, right? I have understood. See, like the redundant bits values are appended as per the Hamming code rule. So this is the entire data to be sent, or this is the code word to be sent. Right? Receiver receives this code word. How receiver will identify the error and will correct the error, that is our next part. I have understood, right? Yeah. Before proceeding the receiver side, just have a look at the entire procedure for Hamming code at the sender side. We will proceed. So take 2 minutes. Don't take much more time. Take 2 minutes. Just look at from first rule to last one, right? From first to the last one in at the sender side. Then we will proceed to receiver side. Yes, can we proceed further? Is there any doubt so far? Yes, can we proceed further? Yeah. So now receiver receives in fact the entire code word, right? So now we will try to understand the receiver side, how correction will happen, how detection followed by correction will happen. So now the receiver side. At receiver side. So receiver side, a receiver receives the code word. Yeah, can you tell me now the receiver receives the code word? Yeah, can you tell me that code word? 11 bits, right? 11 bit size, right? Entire 11 bit size. Yeah, can you tell me that one?
100
1 0 0
100
1
triple
0
01
0
zero.
1
double
0. So 1 2 3 4 5 6 7 8 9 10 11. I have understood, right? So as you already know, this is in fact the red color. 1 2 4 5 6 7 8. 1 2 4 8 are your redundant bits. Already sender and receiver already know about that code word, right? Same rule, Hamming code, both are follows Hamming code rule. So the powers of two positions are the parity bit positions or redundant bit position. Already know. Just I marked to make you more to that attention, right? So now at receiver side, receiver also will do the same computation. See, like for computing P1, you have considered the all bit positions whose LSB is 1. Same scenario. A receiver side, receiver is also now considers all bit positions whose LSB is 1, right? In the binary representation only. So what are all the bit positions I have to consider? Yeah, can you tell me now? What are all the bit positions? 1, 3, the first, right? P1 related. 5,
6 7
not 6, 7, 9,
11
11, right? So recall that rule. First one, tick mark positions, right? 1, 3, alternative. 1, 3, 5, 7, 9, and so on, right? So same rule here. Consider the P1 related rule. All bit positions whose LSB is 1. So by considering all bit positions, what is the string form? By considering all these bit positions, what is that binary string form? Can you tell me now? 1 0 0 0 1 0. Right? I hope understood. This is related to P1 related. Now the second scenario, P2 related. For computing P2, already sender uses the bit positions whose second bit position from the LSB, right? So what are all the as per the P2 rule, what are all the bit positions I have to consider?
2 3 6 7
2 3 6 7
10 11
10 11, right? So by considering these bit positions, what is the string form? 1 0 0 0 1 0 0 0 only, right? 6 only. 10 11, right? 1 0 6 7 7 6, right? 0 0 2 3, right? 1 0, right? This is about P2 rule. P3 rule, whose third bit is 1, right? As per that P3, what are all the bit positions I have to consider?
4, 5, 6, 7.
4, 5, 6, 7, right? 7, 6, 5, 4. By
0, 0.
considering these bit positions, what is the string form?
Zeros.
All zeros. All zeros. Now, the last one, whose fourth bit is P4.
8,
Whose
9, 10, 11.
8, 9,
10,
10, 11, right? So last 4 bits. By considering these 4, the binary string formed is 1001. I hope understood, right? Now, it computes the parity. Receiver computes the parity. What is the parity? This one? Even parity. This is also even parity. Even parity. Even parity. So if computes the parity, if you see all are zeros, if you see this all are zeros, then the message is not corrupted. Message is not corrupted, right? Assume one bit is corrupted during the transmission. So try to understand now. Assume one bit is corrupted. Which bit will make a like corruption? Think about the 9th bit is corrupted. Rather than 0, assume it is corrupted, it is modified to 1, right? Yeah, now the same procedure, we will, can you tell me what are all the modifications? Here 9th bit is modified. So what is the string formed here? 1, 1, 1, right? Here 9th bit is 1, right? 1, 1, remaining things are same. I have understood.
P4.
So last one also, right? Here 10, 1, 0. Here also
1, 0, 1, 1.
0, 1, 1. As a result, yeah, again compute the parity. Yeah, compute the parity. What is the parity here?
Odd.
Odd parity. This is even only. This is even. This is odd parity. I have understood, right? So now finally you can see here, these are all not zeros, means that the error is detected. Try to understand. Error is detected. By considering this direction, what is the string form here? This direction. You can see all are not zeros, right? By considering this direction, what is the string formed here? 1, 0, 0, 1. I have understood. 1, 0, 0, 1. This we call it as, whatever the string formed, we call it as error syndrome. We call it as error syndrome. Error syndrome, right? So this meaning is, if you compute the error syndrome, if all error syndrome is 0, error is there is no error. Error syndrome is not equal to 0. There is an error. Error is detected, and which bit is it has to correct, right? Before correction, it has to identify which bit is corrupted. Yeah, can you tell me what is the decimal equivalent for this one? 1001. What is the decimal equivalent? This is binary, right? 1001. What is the decimal equivalent? Oh, don't you know the conversions? binary to decimal, decimal to binary.
15.
15. 15 is wrong. Again, recall. We have already written here.
9.
9, right? 1001 is 9. Yeah, if you are assume you don't have confidence, assume you are given binary, right? You already know this is the 1, this is 2. Here the position value is 4. So in decimal, 1, 10, 100, 1000. Are you getting? 100. Are you getting? So the position will be 10 times. Since it is a binary number, the position value will be doubled, right? Here 1, 2 power
8
0,
the next one.
4, 8, right? So now multiply these values. 8 into 1, you can see 8. This is 0. This is 0. 1 into 1, 1. This is 0. Sum it. You can see 9. I hope understood. This is the procedure for converting binary to decimal. I hope understood, right? Means, I think now you can guess. So the 9th bit is corrupted. 9th bit is corrupted. We have already seen right here, the 9th bit is corrupted. Right? So try to work out, modify any bit here, follow the same rule. Assume if you modify the 5th bit, you can see corresponding the binary number here. The error syndrome equal to will be like 101. I hope understood, right? So based on this, in the Hamming code, the error correction will happen. Right? At receiver side, receiver will compute the error syndrome as per the same procedure. Right? It will like the rule for P1. It consider all bit positions, form a string, and find out that string's parity. I have understood it, and computes the error syndrome. If the error syndrome is 0, message is not modified, data is not corrupted. It is not equal to 0, data is corrupted. That is error detection, right? Then which bit is detected? Now compute, if you see that error syndrome, make it to decimal equivalent. You can see a decimal number here. That bit position was corrupted. This is about your Hamming code. To get confidence, I will give one problem in the classroom. The problem is